Thanks everybody for attending the WestGrid workshop 4 session. Today I'm going to introduce the high performance computing in Canada. My name is Erming. I'm from the University of Alberta and work for Compute Canada and WestGrid. Okay. Oops. Sorry, there's some issue in the display. So, okay, but it doesn't matter. I can introduce the outline and schedule for today. So, in total we have 90 minutes. I would split this talk to 2 parts. The first part I will introduce Compute Canada and the WestGrid. And then the second part, I will introduce the high-performance computing technology itself. And between the 2 parts, there is a break, 10-minute break. And at the end of each part, I leave 4 minutes for questions and answers. So, by the way, this slide deck was given in the WestGrid workshop spring session, so which takes normally 2.5 hours. But this time I'm giving only 90 minutes. So I already tailored the slides, but still keep the most of them. So the time could be very tight. So I would go through all of them quickly. Yeah. So and some I mean for some slides I may not afford them. So just for the interested audience to read. Okay. So now let's go into the introduction to Compute Canada sessions. So about Compute Canada, I think many people have already known about Compute Canada. Compute Canada integrates 4 regional high-performance computing consortia across the country, provides a shared HPC or ARC infrastructure. ARC stands for Advanced Research Computing. So it supports world-level leading-edge research activities. Compute Canada aggregates petaflops of computing power and petabytes storage capacity over Canadian high performance networks. It also provides overall services, including infrastructure, application, operation, and user support for nationwide users. This slide shows the consortia of the Compute Canada. So personally, there are over 7 consortia. They are ACNet, CLUMAC, RQCHP, HPC-VL, SciNet, ShockNet, and WestGrid. We are WestGrid. But later, it has been consolidated into 4 consortia: Compute West, that is WestGrid, Compute Ontario, and Calco Quebec, and ACNet, or Compute Atlantic. So now, the existing systems or resources, there are 40 universities, 27 data centers, 50 systems, and in total, about 200,000 cores, which builds up 2 petaflops and 20 petabytes. About 100 research software packages are provided, and around 200 experts in utilization of this high performance or advanced research computing resources for research, to support research. So there are some evolution in the Compute Canada systems. Currently, we are trying to build new Compute Canada systems. They are there will be 4 data centers in the near future. They are GP1, GP2, GP3, and LP. GP1 stands for general purpose. General purpose. For example, GP1 is for cloud system, which is located in UVic, Victoria, and the GP2 general purpose clusters in SFU, GP3 in University of Waterloo. And GP2 and GP3 not only just normal clusters, but also a small portion of a cloud. LP is in University of Toronto. LP stands for large parallel. So Compute Canada will be continually developed. So in future, it will be consolidated into 5 to 10 data centers in the end, and with 300,000 cores and 12 petaflops and 50 petabytes. So this year and next year will be the commissioning new systems and decommissioning older systems. This picture shows the new Compute Canada organization chart. So from which we can see that other than the administration block, there are mainly 2 other blocks, TLC and SLC. TLC is a technological leadership council, and SLC is a science leadership council. So in TLC, you can see that there are cloud team, monitoring team, GP1, GP2, GP3, LP teams, and the network team, platform service team, research support team, storage team. In SLC, you can see the education outreach and training team, visualization team, digital humanities team, bioinfo team, and SPNT team. It's a subatomic physics lesson team. There's also a security council and working group. Cloud service. So I just introduced the basic profile of Compute Canada. The following slides, I will introduce the 3 typical cloud, typical Compute Canada services. They are cloud services and own cloud storage service, and Globus Online, which is the high performance data transfer service. First is the cloud service. As I already introduced, there will be a big cloud system, GP1 in Victoria. But now we already have 2 systems that are providing cloud services for users. They are Cloud West and Cloud East. Cloud West is in Victoria, and the Cloud East is in University of Sherbrooke. This table shows the resources in both clouds. Cloud West has about 40 nodes and 630 cores, 200 terabytes. Cloud East has about 36 nodes and 576 cores, about 100 terabytes Sept storage. You may be wondering how to access this cloud systems. So the URLs in yellow can be logged in can be accessed. So you can use your Compute Canada accounts to access them, to log in. How to get a Compute Canada or WestGrid account? I will introduce this later in the WestGrid part. This is the default allocation numbers. So in default, a user can get 2 instances, that is VMs, and 4 virtual CPUs, about 15 gigabyte RAM, 1 public IP, and 40 gigabyte persistent storage, 2 volumes, and 2 snapshots. This is the quota. OwnCloud is a Dropbox-like cloud storage service. It's just like online storage for users. You don't need a local disk space. It's hosted by WestGrid. It can be accessed by your WestGrid user account and password. The picture in the left shows the server URL, and it's located in SFU. And in default, each user will get 50 gigabyte disk space, and it's daily backed up, and you can access it from a web interface, just like the picture in right showed, and you can also access it with your mobile phones. Yeah. Globus Online is, as I said, is a high-performance data transfer service. This is the URL, globus.computecanada.ca. To use the Globus Online service, you need first you need to be authenticated by a MyProxy service. So after you log in with your WestGrid user account and password or Compute Canada user account and password, you can see the authentication page. So you just use your own user account and the password. You can automatically authenticate it. So there is already a proxy stored in the MyProxy server. So you don't have to worry about this part because it's already simplified. So with this service, you can select existing endpoints, or you can understand this as a site, the interface of the site. So you can select the source site and the destination site, then transfer data between them. You can even build your own endpoint with the so-called Globus Connect Personal. So with that, you can set up an endpoint in your laptop or desktop, then transfer data from your laptop or desktop to a data center. Okay, we just finished the Compute Canada part. Now let me introduce the WestGrid. So as I showed, WestGrid is one of the 4 regional HPC consortia of Compute Canada. WestGrid itself has 15 partner institutions across the 4 provinces. In BC, in Alberta, in Saskatchewan, and Manitoba. Yeah. So overall, WestGrid has more than 40,000 computer cores and about 9 petabyte storage space, about 1,000 Compute Canada users, nationwide users, from 475 projects are currently using WestGrid systems. Yeah, this table shows more details. WestGrid staff is composed of the executive director, Lindsay Seal, and director of operations, Patrick Mann, and some coordinators, such as collaboration coordinator, visualization coordinator, and each site has a site lead and some programmers, system analysts, and system administrators. So we work together to support WestGrid. The following slides, about 10 to 11 slides, I would quickly show you the picture of each site. But since the time limit, I won't go through all the details of each site. Just give you an idea how it looks in each site. So first is Jasper in University of Alberta. So it has 4,160 cores and about 830 terabytes. And then Hungary in UA, it's a single system, just like one computer. It has 2,048 cores and 16 terabyte memory in this machine. It also has a data storage space about 53 terabyte NFS. UBC has a cluster called Asinus. It has 9,600 cores and 450 terabytes Lustre space. UC has one called Breezy. It's a Fed node cluster. It has 384 cores and 16 nodes. Storage, it has 400 IBRIX terabyte, 450 terabyte storage. Lattice in use, UC also has one called Lattice, or Lattice, sorry, 4,096 cores and 160 terabytes. Parallel is also there's also a GPU cluster in UC. The Parallel is a cluster that has the normal CPUs and GPUs. It has 7,056 cores and about 60 nodes with GPUs. 3 GPUs in each node. So, and it has 160 terabytes shared by Breezy and other clusters. Grex in University of Manitoba, it has 392 cores and about 100 terabytes. Hermes and Nestor in Victoria, they have in total it has 4,416 cores and 1.2 petabytes GPFS storage space. Bugaboo in SFU has 4,584 cores, 700 terabytes. Silo in Saskatchewan is a special one. It's a storage site. So it has 4.2 petabyte disk space and about 3 petabyte tape library. It also has IBM Tivoli storage management system for backup. But Silo is gonna decommissioned soon, so we will have a bigger storage site in the future in the 4 new systems. So in each site, we want to check the site status. So in the WestGrid web page or website, we can see if you click on resource, you can see the site status of each site. They can be in different colors. So there's a legend to show that different status, different meaning with the status. green means site is in fully operational, and yellow could be in downtime, and orange it means it's available but with some conditions, and purple means online but may not be so stable. Red means the system is not available. So how to use Compute Canada resources or WestGrid resources? So this slide I list some points like how to apply for Compute Canada or WestGrid account, how to get a grid certificate and proxy, which site is good for what. I also introduce something like the recollocation and software packages and technical support, how to get us support. So, okay, first, how to get a Compute Canada or WestGrid account. There are about 4 steps. First, if you are a student or team member of a project, first you need to ask your PI to apply for a Compute Canada account if he or she doesn't have. Normally, she or the PI should already have an account. Then you yourself can apply for a Compute Canada account as part of your PI's project. Then your PI will get an email to see if he or she will approve or reject your application. So normally he or she will approve it. Then you can apply for a consortium account, such as WestGrid or ACNet, or all of them. Please be noted that it normally takes a couple of days for your account to be created or activated. So please don't make a fuss if you don't see it right away. Yeah. The pictures in right shows the sign-in web page and the ones for applying for the consortium account. So the URL in the bottom is the link that shows the details to guide you to do the application. Okay, grid certificate. So other than the user account, sometimes you need to access grid resources, such as you want to use Globus Online, or you want to transfer data, use something like Grid FTP or GCP. You need a grid certificate. So in this web page, in the WestGrid portal.westgrid.ca, you can click on request a grid certificate. Then you can download your grid certificate and a private key. Normally, in a WestGrid machine, it's already there. I think at least in Bugable, you can in your home directory you can see them. Grid proxy is a kind of a proxy certificate that for delegating somebody to do something for you. For example, it has a limited lifetime and a limited privilege. Normally, you just need to run myproxy-log-on in any WestGrid machine. Then you can get one proxy. So then you can do some grid activities. Yeah. Resource classification. So we have so many sites. You may be wondering which site I should use. So this table shows which site is good for what. Okay, for example, the serial jobs can be running on Bugaboo, Hermes, and Jasper, and parallel can be run on Bugaboo, Nestor, Osnus, Parallel, Grex, Jasper, etc. And Hungary and Breezy, they are good for SMP parallel jobs. Parallel is good for visualization. Grex has Gaussian deployed, and Osnus and Jasper Hungary have MATLAB, and the storage data can be stored in Silo and Bugaboo or big data. Okay. So then is software. To run your program, sometimes you need some software or libraries. So WestGrid has both free and commercial software. You can use them. First, you can try to search a certain software package from the website. This is the URL. So if you cannot see the software you want, you can send email to support@westgrid.ca. So this is the mailing list for all kinds of questions. But before you send a question, I would strongly recommend that you check the WestGrid support webpage to see if there's any information you need. At the last of this part, I would introduce about the resource allocation or the new resource allocation. So currently, Compute Canada is building up a new resource allocation policy. So since it's just in the initial stage, I won't introduce too much details, but want to give you some terminologies to help you to have a basic idea about this. First is RAC. RAC stands for Resource Allocation Committee. It's dedicatedly for reviewing and allocating resources for users. RAC allocation includes two parts. First is RPP, and the other one is called RRG. RPP stands for Research Portals and Platforms. If you apply for RPP resource, the scientific and or technical review is needed. RRG, if your requirement doesn't really fit the RPP, you need to apply for RRG. It stands for Resource for Researcher Groups. With RRG, there could be more scientific or technical reviews. There's another one called RAS, Rapid Access Service, which is formally called default allocation. That means in default, you can get a certain amount of resource, small amount, so no scientific and technical review needed. Any questions can be sent to rac@computcanada.ca. So this table shows the RAC schedule, from which you can see that the RPP NOI notice of intent has already started in this month. The RRG and the RPP submissions, the deadline is in November 24th this year. Technical reviews will be in November and ended in December. So in the end, results will be awarded in April if it's April next year if it's approved. So first, what is HPC? There could be many definitions of about high performance computing, but I like this one that I got from Wikipedia. It reads that HPC most generally refers to the practice of aggregating computing power in a way that delivers much higher performance than one could get out of a typical desktop or workstation in order to solve larger problems in science, engineering, or business. So yeah, HPC aggregates computing power to resolve big problems. That's our goal. Before you introduce each part of our components of HPC system, I would introduce two concepts. One is called capability. The other is called capacity. Capability computing is typically thought of as using maximum computing power to solve a single larger problem in the shortest time. For example, a real-time weather simulation and prediction application. While capacity computing, in contrast, is typically thought of as using multiple cost-effective computing power to solve a bigger number of small problems or a small number of big problems. For example, there are tons of users access to a web service simultaneously. Or in HEP, high energy physics, to analyze a huge amount of data, normally we can split them into many small pieces and then distribute them across multiple cluster nodes to process. Yeah. So in the WestGrid or Compute Canada systems, we can see we have a spectrum from capability to capacity. For example, Hungary is the one with maybe the highest capability. It's a single system with 2,048 cores and 16 terabyte and the high-speed interconnect in one system. So it has the highest capability. And Bugaboo and BlueGene can have more capacity because they have more nodes. For example, Bugaboo has 256 nodes, and BlueGene Q has even more. It has 4,096 low power nodes and 65,000 processors. Breezy is in the middle of this spectrum. It's a kind of a fat node. What is fat node? Because each node has big memory. It has 256 gigabyte memory in each node, and it has also many processors in the node. Yeah. Okay. Architectures. As we know that processor and the memory are the two core components in a computer. So there are different ways of classifying the architectures by processor or by memory or by something else. So here we can see that by processor there are some architectures such as SMP, DSM, MPP. SMP stands for symmetric multiprocessors. DSM, distributed shared memory, and MPP, massive parallel processors. By memory, there could be UMA, NUMA, COMA. UMA stands for uniform memory access. NUMA, non-uniform memory access, and COMA, cache-only memory access. This slide shows the evolution of architectures. For example, message passing UMA, NUMA, until comma. Message passing, yeah, just like we're using posts or mails to exchange data, or let's, for example, in a chain store, we use post or mail to exchange goods, products. And UMA, we want to build a warehouse centrally for all the stores. Then use just a low-speed road to transport them. There could be lots of traffic jams with the centralized warehouse and low-speed road. So later, we try to divide the warehouses and then use a highway to connect them. So that's NUMA. So we use a high-speed interconnect to connect different local memories in different processes. So then the data exchange rate will be much higher and no much conflicts. So comma is a kind of a variation of NUMA. So there are only cache-only memories, no local memories. So the difference from comma and NUMA is that with NUMA, it has a so-called static home node. So every time you want to access a data, you need to contact the home node and copy the data. But with comma, you just migrate the data. You don't keep multiple copies. So it reduces the overhead. Okay, programming model. So normally there are two programming models, serial and parallel. Serial means instructions are executed one after another on a single CPU. Parallel means computations are carried out concurrently on multiple processors. There are normally there are two parallel programming models, SPMD and MPMD. SPMD stands for single program multiple data, and MPMD multiple programs multiple data. Yeah. There are a few tools for each programming paradigm. For example, in data parallel, the HPF high performance Fortran is good for data parallel, and OpenMP, Open Multiprocessing, is a tool for task parallel, and PVM and MPI are good for message passing. There are even some hybrid ones. For example, MPI plus OpenMP and MPI plus GPU, CUDA. And some even advanced tools like Chapel and Pegas, that is partitioned global address space. Okay, so I just introduced the processor and the memory, the core part of a computer system, and the programming model. Then is the interconnect. What is interconnect? It's the part that connects the core components and the peripherals. Like for example, the popular ones like the PCI, PCI-X, and the PCI-Express, and Infiniband. There are even some new ones like Hyper Transport, developed by AMD, and QPI Omnipath, developed by Intel, and NumaLink by SGI. So I will introduce more on PCI-Express, and Infiniband. Yeah. Before that, I would explain two important concepts, serial and parallel. So as you already seen that in the programming model, there are also those two concepts, serial and parallel. But here could be different. So in the interconnection or I/O bus, there are also the two concepts, but there could be in the opposite way as the programming model. So in early days, serial connections are reliable but quite slow. So then we introduced the parallel connections. That means we can send multiple pieces of data simultaneously. Well, later we found that parallel connections have their own problems. The biggest problem is that the electromagnetic interference between wires. So then the pendulum swung back to the serial connections again. So, but it's high optimized. So later we can see the why it's different. Okay, in the PCI and the PCI-X, they are using the parallel connection. So the disadvantage is that the electromagnetic interference and signal degradation are very common in PCI and PCI-X. So there's a bottleneck in the bandwidth of these two types. So later, we developed the so-called PCI-Express interconnection. As it shows, instead of using parallel connection, PCIe or PCI-Express use the point-to-point serial connection that use a switch to distribute this kind of connection, data transfers. So then each device has its own dedicated connection. So in this way, the so-called electromagnetic interference problem is eliminated. PCIe can also be in parallel, but it's based on the switch-based point-to-point serial connections. So we can see that 16 times PCIe connector can reach about 6.4 gigabyte per second. Infiniband is the same idea. So it's also switch-based, point-to-point. It's again, it's changed from the original parallel connection to serial connection. Also added the so-called multiplexing technology. So Infiniband can be thought of as just like you grow the interconnect out of the box, out of the body. So then you can have much better scalability of the interconnect. So because in one box, a fixed size box, you can hardly, it's very hard to scale it, right? But the Infiniband just grow just move the interconnect out of the box, so it has a much better scalability. So we can see that Infiniband has a much higher data transfer rate. With EDR, it can reach nearly 300 gigabits per second. Yeah. This table shows the comparison between Infiniband and PCI-Express. Yeah, if you are interested to read. Yeah. So something like scalability and the kernel bypass, etc. I won't go through the details. Yeah. Next part is about storage. There are first I would introduce the storage protocols, and then I/O bus, and then the redundancy technology, and storage attaching approaches. So in the storage part, we can also see that how can we get a higher performance than the traditional way. Yeah. This is the list of storage protocols, such as CIFS, SMB, and NFS. They are application layer network protocols. Yeah, and SCSI is a bottom level protocol. iSCSI is a kind of a protocol that over TCP/IP, and the fiber channel and the FC and the FCOE. Fiber channel just use the transport protocol, mainly SCSI commands over fiber channel networks. Fiber channel may not be just a fiber channel. It can also be copper. For example, fiber channel on Ethernet, we can use Ethernet, something like 10 gigabit or even 100 gigabit Ethernet to transport fiber channel protocol. Okay, so I/O bus. We just introduced the Interconnect, which connects the CPU and memory and the peripherals. And I/O bus is the part that connects the core components and the data storage. So again, the secret is relies on the parallel and serial models. So we can see there's also evolution in this part, from so-called ATA to SATA, or SCSI to SAS. ATA means advanced technology attachment, or SATA means serial ATA. And SCSI and SAS also means serially attached SCSI. So the picture in the left shows the one we used a few years ago. It's a parallel I/O bus. Still, it has the electromagnetic interference, and there's also cost. It's also costly. So later we developed the SAS or SATA, which can see it's the one shown in red. It has a higher performance. In the figure, we can see. Sorry, the font could be font size could be too small, but I can read it for you. So with the SATA and the SAS, it can reach to something like 6 gigabits per second. Okay. So those are interconnections or I/O bus. We talk about high performance. High performance not only just speed, but also can be high availability and reliability. So RAID is the kind of technology that ensure the availability of data. So RAID stands for redundant array of independent disks. There are many RAID levels, such as RAID 0, RAID 1, RAID 2, 3, 4, 5, 6, or even some nested RAID, such as RAID 10, 1, 0, 5, 0, 6, 0. RAID 0 means striping. but without parity or mirroring. Or read 1 means mirroring, also without parity or striping. Read 2 and 3 with parities. Read 4 also striping with parity. Read 5 striping with a single distributed parity. It's not the parity is not in a dedicated disk. It's distributed. And read 6 with double distributed parity. So this is a picture shows the read 0 and read 1 and read 5. So we can see that read 0 only striping, no mirror. While read 1 it's mirrored, but no parity. Read 5 it's single parity, but distributed. Nested read is something like we do, for example, we can do read 1 at first, then do read 0. That means we can stripe data across disks, then do mirror of them. Similarly, read 5 0, 5 0. We do read 5 at first, then 0 later. Yeah. There's a comparison of all those read technologies. So we can see that some with a high performance, some with a better capacity. Yeah. So it's always a balance between the availability, capacity, and the speed, read and write speed. Yeah. Multipathing is the part, is also talking about the availability or reliability. It's the part between the core component and the storage. So inside a storage, we just talk about read. But how about the part between storage and the core component? So what if it fails? So that's why we introduced the so-called multipathing technology. So from the picture in the right, we can see that we set up multiple paths or channels to connect these data storage. So if one fails, we can automatically switch to another to ensure the availability of data. Yeah. Okay. This picture shows the 3 types of data attaching types. For example, DAS, NAS, or SAN. DAS means direct attached storage, and NAS means network attached storage. SAN means storage area network. DAS means the file system and the storage is in the same box of the operating system. NAS means we have a separate file system or storage and access it from network. SAN means we use a high-speed network to access a high-end storage. For example, we use a fiber channel or gigabit Ethernet to access the storage. Yeah. So with DAS, it's obviously there's a bottleneck for the scalability. With NAS and SAN, we have better scalability and better performance. Yeah. Okay, so then I will introduce the file system. So we just introduced the storage itself and the connection to the storage. Now, what is a file system? File system is the part that connects the storage and also provides an interface for users to access the storage, to access your data. So this is called a file system. In high performance computing, we use so-called parallel file system to gain the high performance. How it works? The idea is that we split data and distribute them into multiple storage nodes and access them with, via high-speed network. So then we can access the multi-storage nodes concurrently in parallel. Okay, so this picture shows the difference. The one above shows the traditional way of data accessing or the file system. For example, NFS. We can see that the metadata and the data are in the same channel. And when client wants to access data, it has to go through the management node and then the storage nodes. While with the parallel file system that is shown below, we separate metadata from the user data, the real data, and then we use some dedicated nodes to transfer data. So clients can access data directly without needing to go through the management node. So it eliminates the bottleneck and increased the data access rate. Yeah, because it's in parallel. Yeah, and the metadata is served by the so-called metadata server. There could be multiple metadata servers. So in this way, we use the parallel. This time, the parallel is, has the advantage. We can have much better performance in this way. Some common parallel file systems like Lustre, Lustre FFS, Orange FS, GPFS, IBRIX, CXFS, Kinesis, PNFS, Google FS, and Sept. Sept is widely used in OpenStack cloud or other open source clouds. This picture also shows how it works in Lustre. Similarly, as I just introduced, they have in Lustre there are separate metadata servers and multiple OSDs to connect to the data storage, and the users, after get the metadata, users can access data storage nodes in parallel directly. Yeah, that's the secret. Okay. Object storage. What is object storage? So traditionally, we just store data and put the metadata in the so-called metadata server. Object storage is a little bit different. It not only stores data itself, but also some extra information such as metadata, OID, some attributes of the data. So it the idea is to move the low-level functionalities such as space management, security functions into the storage device itself, instead of doing it all in the management nodes or metadata servers. So then it significantly reduced the load of the metadata servers. So then we can gain better performance and scalability. Object storage is good for storing unstructured data, such as photos, songs, videos, something like those. There are some comparison of the three storage types, such as file storage, block storage, and object storage. We can see from the picture, we can have a straightforward concept of the difference. So file storage, we just use a file system to organize the data blocks, small data blocks. And the block storage, we transfer data in big blocks, which could be very fast. And the object storage, each data is kind of wrapped into an object with OIDs, metadata, part of the metadata, and the attributes. So again, we can see some difference between the three storage types. The main point here is that the cost and performance difference between the block, file, and object storage types. So we can see that block storage can have the highest performance, but it could be costly. Object storage could be locally could be slower, but it's cheaper, and it has very good scalability. So with multiple objects storage connections in parallel, so you may finally gain much better performance than the traditional ways. Yeah. Okay. The last part is about evolution of computing. I will go through something like mainframe, cluster, grid, cloud, big data. To give you a straightforward idea of each kind of technology, I want to use one word or one phrase to describe them. Mainframe is just like something like a superpower. It's quite powerful. And cluster could be like lots of workers. Grid can be thought of as global orchestration across multiple nodes, multiple distributed nodes. Cloud tries to turn everything into a service. And big data is something like finding a needle in the sea. Yeah. Oh, sorry. Okay, this slide shows the evolution of the computing. Yeah. But it doesn't mean that the old ones, the one below, is replaced by the one above. It's just different technologies. All of them are still in use. Yeah, just different types of applications. Depends on different scenarios. Okay, first mainframe. Mainframe was originally referred to large cabinets that housed powerful CPUs and shared memory. There are some modern design in mainframe, such as high-speed connection and high availability and security, extensive I/O facilities, and use something like virtualization technology to support massive throughput. Yeah. Clusters. It's basically just tightly connected computers. Just we can use normal computers or blades to work together as a single system. It's low cost, with better scalability and flexibility. Some key technologies in cluster are something like batch job scheduling and management and parallel computing. Grid computing is the coordination on massive computer resources from multiple locations to reach a common goal. The resources are normally loosely coupled or could be heterogeneous and geographically dispersed and dynamic. Sometimes it's available, sometimes may not be available. Some main features in grid, such as high-level scheduling, workload management, unified security infrastructure, globally organized information system, and virtualized organization, transparent data transfer interface. Yeah. For example, this is the biggest grid in the world, which is called the WCG, the worldwide LTC computing grid. It has about 300 sites in the world, in different countries, about 50 countries, I think. Yeah. So it's try to analyze the data produced from the Large Hadron Collider. Yeah. Cloud, as I said, is a kind of a technology try to turn everything into a service. For example, we want to turn the infrastructure level of computing resource into a service, or a platform as a service, or software as a service. There could be more, something like hardware as a service, network as a service, database as a service, communication as a service, or business process as a service. Eventually, it could be everything as a service. So what does as a service mean? It can be just simply thought as just we try to provide such kind of a service quickly for users. So users don't have to worry about setting up, deploy them. Users just use it. Yeah. Just like you use the utilities, you use power at home. You don't need a setup of a factory yourself. You don't know where it is. You just use it. You just plug into the socket in the wall. You just use it. Yeah, this is the goal of the cloud. Yeah. Okay. This picture shows the three basic level of cloud service. They are infrastructure as a service, platform as a service, and the software as a service. There are some examples, like the infrastructure as a service. You can use OpenStack Cloud, or VMware, or Amazon. They are providing VMs for users. VMs means virtual machines. So for users, there's no big difference. It's just machines. It's just like you can still use not so different from you use as your desktop, laptop. Platform as a service, something like Google App Engine, Windows Azure, or MySQL also develops platform as a service for users. And software as a service, something like Gmail, something like Oracle or Salesforce. They are providing some services for users, so you don't have to buy your own machine. You don't have to have your own platform like a database. You don't need to set up your own mail server. You just use it. Just you use it, Google Mail online, yeah, or Google Docs, Google Drive, spreadsheet, yeah, blah blah blah. Yeah. This picture shows the evolution of the from the traditional IT to IaaS, PaaS, SaaS, and XaaS. That is everything as a service. So we can see that in the traditional IT, we need to do nearly everything, from hardware installation, networking, storage installation, and then operating system installation, and then deploy some software, and then run some applications. But then with the IaaS, you don't need to do the physical part. You only need to install your software and then some platforms, and then you can run your application. Well, with PaaS, platform as a service, you don't need to even deploy your platform, such as the database or some development environment, like for example, LAMP, the PHP or something. You don't need to deploy them, just use them with PaaS. SaaS, so it's even further. You don't need to install your own software. You can just use them, yeah, online. And XaaS, so you will, with SaaS, you will only focus on your own business. You don't even need to take care of your own VMs. You don't need to take care of your own servers. The one example is called Amazon Lambda. With Lambda, you don't need to maintain a server online. You don't need to maintain a VM by yourself. You just use develop your own code and then run it on Lambda. Yeah. So this is a kind can be thought of as a good example for XaaS. Okay. Last one I would introduce is about big data. First, what is big data? It refers to a technology of handling data that is too diverse, fast changing, or massive, or for conventional technologies to address efficiently. So today's new technologies make it possible to realize value from big data, because we have high performance computing technologies, high performance interconnection network, yeah. So make it possible to do big data analysis. Big data has normally has four features. We call it the 4 V's: volume, velocity, variety, and veracity. Volume means the data is very big, and the velocity means the data is in motion, is changing, and variety means the data can be many types of data, many forms, and veracity means data in doubt. So with uncertainties, we could be inconsistent, could be with some ambiguities and latency, deception, etc. So with this kind of features, how can we efficiently analyze, do analysis on the data, on the big data. This is the goal of big data to address. The core technology of big data is the starting from the stone that were developed by Google. They are the three famous ones: GFS, MapReduce, and Bigtable. And MapReduce is the core part. And later, there are some free versions. For example, developed by the most famous one is developed by Apache. That is the Hadoop technology, including HDFS, Yarn, HBase, Hive, Pig, lots of them. So we can see that in the picture, we can see that HDFS is to store data storage, and then MapReduce to do data processing, and Yarn for task and resource management, Pig for data access, HBase for orchestration. This picture shows the basic idea of MapReduce. So we can see that in the text, for example, we want to count how many letters of each. First, we split them, then map them to different nodes, then shuffle them, then reduce them to count. That means we count them. Like we have 2 bells, 3 cars, 2 deers, and 2 rivers, and then finally we integrate them to output the data, the result to users. Big data, even big data has evolution. The new Troika is still developed by Google. They are Dremel, Pergel, Caffeine, and also free. There are some free versions like Apache Drill, Apache Giraffe, and Stanford GPS. So this is a good example to compare the older MapReduce technology and the Dremel. We can see that to analyze 87 terabyte data with 85 billion records across 3,000 nodes, we can see that we just do a simple count. We can see that with MapReduce, it takes about a few hours or a few minutes. So the one with record-based is rule-based takes a few hours, while the column-based one takes a few minutes. While with the Dremel, it only takes a few seconds. So there's a big difference. Yeah. The last one I will show you the big data ecosystem. You can see there are many tools in big data. So other than Hadoop, there are some new ones like Spark, Flink, Storm for data processing, and Neo4j and Giraffe for graph processing, Cassandra, Kudu for big data database, and MongoDB, Redis also database. Also some SQL engine like Apache Drill and Mahout. Also, there are some new technologies like containers. So Docker, Martian, Mesos, and even Kubernetes developed by Google. They are trying to set up microservices framework for analyzing big data.
Hi, Erming.
Okay.
Don't mean to interrupt, but just to note that we're getting near the end, so I just wanted to double check with you and see if you were close to wrapping up, or just to give
yeah,
people an idea of how much
the
more,
last,
or if you wanted to take any last
slide.
questions.
Okay. Yeah, okay. So just to quickly summarize it. So I introduced Compute Canada and WestGrid. Then I introduced the high performance technology, such as the architecture, memory, interconnect, and then evolution of the computing technologies, such as mainframe, cluster, grid, cloud, and big data. Okay, so my colleagues will give some more detailed hands-on practice about using WestGrid and Compute Canada resources. So, yeah, if there are any questions, you're very welcome to ask. Yeah.
There was one that we received from the web stream that asked if you could explain some of the technical terms used earlier in the presentation, explaining the difference between SMP, DSM, and MPP.
Okay. Let me check what it is. Yeah. Yeah, SMP means symmetric multiple processors. DSM is the difference is that it's distributed and shared memory. And massive parallel processors means this kind of architecture is kind of a big array of processors, very big array of processors. Yeah, so that's the main difference. Yeah, this is just different types, forms to organize processors and the memory. Yeah.
Can I ask a question, please?
Go ahead, please.
Yeah. My question is regarding the parallel and serial code you mentioned. So as you talked, it seems that right now, these days, maybe the serial codes again they work good. Actually, you know, I had an experience with the GPU code. I had the GPU code, and we tried to run it on parallel. Then the specialist who was a high performance computing center of UVic. He told me that the program is not efficient because it goes, I mean, a lot of time between CPU and GPU, so it takes time and it is not efficient. So with what you said, I mean, is it better maybe these days to write again like the serial codes with the PCI-Express you mentioned, or again like the GPU or parallel code, they works well? Or if you explain about this, then I appreciate it. Thanks.
Yeah, this is a good point. Yeah, we know that with GPUs, will have a better performance because there could be many cores in a GPU, but the price that you need to transfer the data from CPU to the GPUs, and it depends on your application, your program. If it's coded well, you can reduce the serial part, and you can put mostly on the parallel part. Then you can get the performance. Otherwise, you sacrifice the time. You could be even worse. So that's the tricky part. About to use a PCI. I wouldn't say PCI, but the PCIe is a good point, good selection. You can still use this. Yeah. But we're talking about a different part because GPU is the processor, and PCI is the part to access the data, right? It's a little bit different, but still, this is a good point. I think PCIe is still very good. It also evolves. Nowadays, the highest speed of PCIe can be comparable to other technologies. So yeah, it's I think it's good. Yeah.
Yeah. Thank you. Thanks very much.
Thank you. Yeah. Any other questions?
And just one quick question: which machines they have like the PCI-Express on it? I mean, which of the system you mentioned?
I think all the new systems, all the existing systems have PCIe. Yeah. The PCI-I or PCI-X is the older technology, already obsolete. Yeah, I think. Yeah.
Okay, thanks.
Yeah, you're welcome. Because in this presentation, I just want to compare the new technologies with the older ones, so to show you guys how can we get higher performance, why we call it high performance computing. Yeah.